So it's very pleasant. That was very pleasant. I was able to write my talk on the train, and thank you for coming. I will, as Paul said, I will talk a little bit about sensor networks, but first I'm going to talk about Snowcover and climate and some of our research using satellite remote sensing, and then how we integrate that with new sensor networks that we're starting to deploy in the Sierra Nevada. First, a little background on Snowpack and climate. Many of you are already familiar with this, but just to bring us up to speed, about 2/3 of the Sierra Nevada precipitation is snow. Now, much more in the southern Sierra, which is higher elevation, where most all of it's snow, as opposed to the northern Sierra, which is lower elevation. But a lot of that snow falls when temperatures are around 0 degrees. So a very small temperature increase, climate warming, will turn, basically a 3-degree increase in temperature would turn about 1/3 of that current snow into rain. And as indicated on this shaded map, the Sierra Nevada going up into the Cascades are the warm snowpacks. Colorado, Utah tend to be colder snowpacks and not as vulnerable. Also, a 3-degree increase would mean earlier snowmelt. It would shorten the winter by about 2 months. And a 3-degree increase would also turn some of these big snowstorms into rainstorms, causing flooding when you don't expect it now. That's just from existing data. Another perspective that I stole from Lester Snow, the head of the Department of Water Resources, is just a quick comparison of how much water is stored in the snowpack. 14 million acre feet. Now, some of you are not water engineers, but envision an acre a foot wide. So 14 million acre feet of water is on average the snowpack storage. That's larger than the reservoir storage behind dams in either the Sacramento or the San Joaquin Valley draining out of the Sierra Nevada. So there's a likely loss of that snowpack storage capacity, which there's no obvious way to make that up for seasonal storage in the Sierra foothills. Now, existing snowpack measurements, because the main question that water agency managers ask every spring is how much snow is out there, because they have to make commitments for water deliveries. Farmers need to take out bank loans. They need to plan for floods storage behind their reservoirs and so forth. And they use an operational network that has several hundred stations across the western U.S. And when you look at a map like this, it looks like a pretty dense network, but especially in the Sierra Nevada. But often the error in estimating the amount of snowpack and thus runoff that occurs is 20 or 30%. In the southern Sierra, they have it down to about 10% in most years. But even that 10% error is a lot of revenue if the water could be put to use or could be committed for delivery or is committed and doesn't appear. So they're pretty good at predicting the mean, but when you get to the extremes, the uncertainty goes up. So this measurement system, which looks pretty dense, is actually not very dense when you zoom in to a normal-sized river basin, which drains to a single reservoir. I've highlighted the Merced and Tuolumne river basins here and focus on these green diamonds, which are I call them the snow pillow sites. That's where we have continuous measurements of snowpack and other, there's weather stations there too. And in the whole Merced River Basin, Merced River, of course, Yosemite Valley is right here in the middle of the Merced River Basin. There's only 3 stations in the Merced River Basin. In the Tuolumne, there's 7, but it's about twice the size of the Merced River Basin. And these stations are are not representative of the topography. They're simply index stations that are used for statistical relationships between total seasonal runoff and how much snow is at the index station. So they're not designed to give quantitative estimates of snowpack. They're designed to give statistical relationships, and they're, again, pretty good at predicting the mean. They fall down when you get to the extremes. And if climate is not stationary, that is, as we have climate warming, then you're outside the range of your statistical relationships. So you need another 10 or 20 or 30 years to build good statistical relationships again. So there's interest even using existing decision support and having better measurement systems, let alone have the ability to implement a new generation of hydrologic forecasts and hydrologic models. Okay, now let's blend ground-based and satellite data. So you get an idea of the problem by looking at this photo, which I actually just took from the parking lot of the Bear Valley ski area. And the question, how much snow is out there? Well, in this photo, there's no measurement. There's no measurements anywhere you can see in this photo. But with satellite, we can tell the fraction of snow cover in an area. But we can't determine the snow depth. So I'm going to show a time series of some work that I do in collaboration with Jeff Dozier at Santa Barbara and Tom Pater from University of Utah on classifying MODIS satellite data for estimating snow cover. In this image, you see a bunch of squares which are 500 meters on a side, and I've shaded them white if it's 76 to 100% snow cover, and in darker shaded black if it's 1 to 25% snow cover. So this is day May 10th, 2004 in the Merced and Tuolumne river basins. Yosemite Valley is down here. Tioga Pass is up here. So I'm going to scroll through a little series so we can get good snow-covered area, and this is sub-pixel information, so I won't go into the algorithm. You can ask me later if you're interested in how it's retrieved from this multispectral MODIS satellite. But it does give fraction snow cover in a pixel from the reflectance spectra of the different wavelengths. Moving ahead, May 11th. Now, I bring this one up because there's a bit of a problem. The satellite's not looking straight down. It's looking off to the side, so everything's distorted by quite a bit. But still, it's useful information. There's some more distortion as I go through this time series. Here, there's some problem with clouds, areas that are not snow. The ability to distinguish between clouds and snow is pretty good, but not perfect. Some cloud problems here. My colleague, Jeff Dozier, and my associates at UC Merced have developed means to filter this data to extract the useful information and to interpolate between scenes, because we have no scenes when it's cloud covered. We have only data when it's cloud free, but we have a lot of partial scenes when it's cloud covered. So there are also sensor noise, data dropouts sometimes. These are NASA satellites. They're not operational, and so operational quality, so there's always some possibility for data loss. There's the off-nadir viewing, especially in the forested areas. So your raw snow cover, if you have a scene, which is a vertical plane here, if this is on the ground at XY directions, well, actually, this is turned on its side. So this would be, just think of it as a XY time axis here. So if we have a scene that has partial information and another scene that has partial information and several of those, how do we interpolate that over space and time? Again, I won't go into the algorithms that are used to do that, but simply show some filtering. Oops. And I'm going to, let's see. Okay. Look at the bar here. This is a different color for snow cover, zero snow cover, going over to complete snow cover, fraction between 0 and 1. So again, in each pixel. And this is simply an XY elevation projection of the land surface area in the Tuolumne River Basin. And so higher elevations appear up here, lower elevations down here. So dark green is no snow cover. As you go into brown, it's more complete snow cover. So on the left, you see the raw images after they're not raw images, but processed images directly from the satellite, where we've used the spectral unmixing algorithm to estimate the fraction snow cover in the scene. And then on the right is the filtered product. So I'm going to start this, and this goes from October 2004 through July 2005. There's a counter down here. So we see that as it goes into October, we're starting to get snow cover at the higher elevations, no snow cover at the lower elevations. Snow cover, the snow-covered area fluctuates a little bit as we go into February, March, and as we go into April, then the snowpack starts to recede and then disappears as we go into July and August. I'll play that series once more. As we go into October, we see we got some early snow that year. Notice the left, that's the actual raw data that's being used to filter and get this other time series. It's also interpolating for snow under clouds. So we can develop these retrospective time series for snow-covered area, which is great for research and process level studies. It's not necessarily what people who are making forecasts want. They want to look ahead, not back. But let me go ahead and give a few more diagnostics on this snow-covered area. Now, plotted here, I have a time series from March 2004 through October 2004 for the Tuolumne and Merced River basins. And the ordinate is snow-covered area, so fraction of snow-covered area, and each line is an elevation band. So I've separated the basins into 300-meter elevation bands, or 1,000-foot elevation bands, and we see the fraction snow cover. So at the highest elevations, we see there's fraction snow cover is near 1 in March, and then it declines down to 0 sometime around September. At the lowest elevation band, 1,650 meters elevation, it only gets up to about 25% snow cover and is depleted by sometime in April. So this is 2 different years, 2 different basins, but the patterns are similar. And this is not the filtered data. This is the data before filtering. So you do see some bumps in it. So 2004 was a below average snow year. 2005 was a well above average snow year. And some features of what the Snowpack and the Sierra Nevada does, I think, are well illustrated here. Each successive 300-meter elevation band melts out about a month after the one below it. And in 2005, which was a heavy snow year, basically about double the snowpack, each band melted out about a month later than it did in 2004. So although think of these last two as the really high elevations, so look at, say, this line, these 2 lines here, which are the mid elevations, melting out sometime in July. Down here, they're melting out in August or September. And so far, I've only done this analysis with the 2004, 2005 data, but I think this really covers a good range of snow conditions to see this consistency and the timing of the melt out. And it's consistent with modeling too. Now, let me go back, because for the water managers and for many other research purposes too, we want not just snow-covered area and to know when the snow cover is depleting, but snow water equivalent. How much water content is out there in an elevation band, in a water basin? And the only measurements we have are these. Again, these green snow pillow are the ones that telemeter data continuously, most of them via GOES satellite. Whoops. These red circles are manual measurements done monthly. So they're good for a once-a-month forecast, but you can't update it in between there. And these yellow ones are also, the yellow circles are also telemetered, but they're on the east side of the Sierra Nevada, not the west side. So these are the only measurements we have. So we estimate snow water equivalent by interpolating these to create a surface. Even though they're not necessarily representative, that's the only measurements available. When you interpolate them, and they give continuous measurements, so this is snow water equivalent for 2004 in the Tuolumne Basin, January through July. We see that the interpolation gives us about the same amount of snow water equivalents here, 0.4 meters, 0.6 meters, up to about 0.75 meters. And there's not that much difference in different elevation bands. Well, that's actually because all the sensors are right in the middle elevation bands. There aren't any real high and real low out in the mountains. But then you do get a little bit of discrimination, because even though there's small differences, the lower ones often do melt out faster than the higher ones up. Now, the lower panel shows what happens when I take this surface and correct it for fractional snow cover. Because when you interpolate these ground measurements, you get snow everywhere. But with the satellite data, I can mask out the areas without snow or with only fractional snow. Then, of course, this is transformed. Basically, this graph times this graph gives you the bottom graph. So we get the discrimination in snow water equivalent. So that's then the snow water equivalent corrected for fraction of area that has no snow. So it's an equivalent snow water equivalent. So we see the discrimination then. And that is a product that we've used multiple times. Yeah. Question?
February spike in the product.
There's a February spike in the product. Oh, I don't see it. It's before that graph. It could be any of three things. It could be snowfall, but it doesn't, because it does show up across the elevation bands. So it's probably snowfall. It could be some sensor noise that we haven't, because these are the unfiltered data. We're putting out a paper which will have the filtered data in it, but I don't have those figures mature enough to show you yet. So I don't know if that's snowfall, and I think it's probably filter. I mean, I think it's probably something to do with this. The snow-covered area data has a lot of noise, as you saw. Okay, so we've produced this product. We've distributed it to some water managers. They found it somewhat useful because it's another data point on estimating how much snow is out there. But everybody knows it's not real accurate. And why is it not real accurate? Well, when we go out to one of these operational snow pillow sites where snow is measured and do a snow survey, and the snow surveys that our group does, we typically we go out with a long pole and measure snow depth at about 100 points or so on a grid. And then we measure snow density at 2 or 3 points, because snow density doesn't change much, but depth varies, from here to here. It measures by a factor of 2 or more depending on where you are, just a few meters away. So there's tremendous variability. So what I'm showing here are two graphs from snow surveys that we did at at the snow measurement site that's between the Tuolumne and the Merced basins. It's on the ridge between them. The snow course, or the operational site, was measuring about, in this case, 85, in this case, 92 or so centimeters of snow water equivalent. our survey mean was down here at about 65, and this was a grid around this snow pillow site, and here it was about 65 centimeters. And this is just the mean and range of all the values shown on this box plot. So, and we've done this at a lot of snow course and snow pillow sites. So we know that if the snow pillow site reads the true mean, it's fortuitous. They weren't designed, and they don't give you the representative values that you need. Now, there's ways we can make them more representative by deploying more sensors, and I'll talk about that in a minute. So, for research purposes, we adopted another approach to accurately estimate the snow water equivalent across the basin, everywhere across the basin. And from that, we can also construct an energy balance on the basin, because that is incoming solar, outgoing long wave, and then the turbulent terms of the energy balance. Or we can just use a temperature index. And what the data I'm going to show you are just simply based on the temperature index. Again, we're doing the full energy balance, but that's a little more complicated in this time frame to explain to you. So I'm using the simple temperature index, which is another way of estimating snow melt. So I can determine on a daily basis, just from the temperature, knowing the temperature across the basin, the potential snow melt per elevation band, or per every pixel in my basin. And then I can apply that to every snow-covered scene, every snow-covered pixel, until the snow melts out, and I estimate how much snow had to be there because I know how long it took to melt out. So therefore, I can back up. I can run this calculation backwards and figure out how much snow had to be there at the beginning of snow melt in order for it to take however many days it took of whatever temperature it was to melt out. And I believe that to be the most accurate estimate existing of how much snow is out there in the basins. And and again, I didn't use an energy balance. I simply went to sites where we're measuring both temperature and snow depth on a daily basis and fit a regression to get my temperature index. And this just tells you that the conversion factor between temperature and snow melt changes during the season. This is strictly an empirical relationship. But it's intuitive because you think, well, the energy balance changes too during the season. Okay, so when I run that calculation, again by elevation band, you get a time series here from March through October 2004. And this is the volume of snow melt that occurred, running back to give you how much snow there was. So the total amount of snow melt across all the elevation bands is at the top here, about 50 times 10 to the 7th cubic meters of snow melt in the basin. Then the distance between each of these lines would be the distance in that elevation, the amount of snow that melted in that elevation band on the landscape. So we see that in 2004, most of the basin was melted out by sometime here in July, but this higher elevation was still contributing snow melt, and that top line is actually sloping up even through September. Well, that's the snow melt that's providing the base flow in the streams, some of the base flow in the streams, higher elevation streams, even late in the year. We see the lowest elevation didn't contribute that much, and it melted out very early. So just the equation used, the melt flux is equal to some index of temperature. It's actually the degrees above zero times the duration that it was above zero times the empirical factor from the previous slide. So this is the amount of snow melt that occurred, and thus the amount of snow that had to be there at the beginning in order to produce the melt and to produce the snow cover depletion pattern. Now, let me take a subset of that previous graph, and just from March through July, this is the same thing, but only part of the melt season. It's just the part when the melt was occurring in most bands. And the bottom one, I took my previously estimated snow surface from my interpolated ground-based measurements masked with the satellites. So that was my estimate of how much snow was out there. And I applied a snow melt model to that, too. So so I had two initial conditions, one estimated by the energy balance, I'll melt it, one estimated by the ground-based measurements, I'll melt that, and they're quite different because they had different starting quantities and because they give different, because there's different amounts of snow in each elevation band from each condition. Basically, my interpolated ground-based measurements melt out a lot faster in this case than the actual snow melt. So the snow pillow sites may be melted out at a certain elevation band when there's still a lot of snow in that elevation band or similar elevation bands. Not surprising because, and the same thing happened from the Merced Basin. So showing this is the Merced Basin 2005. So it melts the snow too fast and it actually underestimates the snow. Now, let's look at how much snow was contributed by each elevation band then. So this is, on the abscissa is elevation band. Again, these 300-meter elevation bands. The numbers indicate the elevation at the center of the band in meters. And the right-hand red bars in each graph, the top graph is the March through September, the whole snow season. So the right-hand red bars are the catchment, the fraction of the catchment area that's in that elevation band. So we can see most of the elevation is down here in the 2,100 meter to 2,700 meter elevation and up to 3,000 meter elevation. This is the main snow producing area. The black bars then indicate the amount of snowmelt, the fraction of the snowmelt that came from that elevation band. And we can see the higher elevations contribute snowmelt way out of proportion to their area of the basin because they're colder and they accumulate the snow, they get more snowfall. And especially during June, and it would be even more marked during July or August, where the higher elevations are basically contributing all of the snowmelt. Now, all of our measurement sites stop at about this elevation. They're in basically this elevation, this middle elevation range. So the findings from this analysis was that 36% or about 35% of the snowmelt in these two basins came from above 3,000 meters, where we don't have any snow measurements, and that is grossly underestimated in any quantitative basin estimate that you make with this snow pillow and snow course data. Skipping down to the bottom, the second bullet then, 13% is from elevations below where you really have, in these two basins, below where you have snow course measurements. Now, in some basins, the snow course measurements go lower, but in this basin, they didn't. And only about half or little more than half of the snowmelt came in this middle elevation range. So that middle elevation range does produce most of the snowmelt, but not all of the snowmelt. So this is based on just so far 2 years of data and 2 basins, but we believe it to be a fairly general result, and it has implications for then upgrading of infrastructure to measure snow in the mountains. It has implications for how what we think the water balance, where the snow melt is going, because we've estimated there's less snow out there, and that's correlated with actual stream flow. So somehow these statistical relationships that have been developed over the past account for the measurement error that appears to be quite large. And also, now, we showed that we can estimate what I think is accurate estimates of snow across the basin using a temperature index, or even better, an energy balance approach, where we back calculate through the snow-covered area time series. That's great for researchers because we can do retrospective analysis, but water managers say, well, the thing I really want to know is not how much snow was there 3 months ago. I want to know how much snow is there now. And that question we can't answer with this method. So that leads to needing a better ground-based network. And so we're starting to deploy, we think from doing all of our snow surveys, we think we understand where to measure snow statistically across the landscape. Given the physiographic and vegetation variability, where should you measure snow is not a trivial question, but we have enough data that we think, at least we have ideas that we're testing now for that. So together with a number of colleagues, we're deploying snow measurement at where these white stars are. I put this gold star on there because that's also, I think Jim Kirshner and colleagues here from Berkeley are deploying things at Sagehin on the east side of the Sierra Nevada. But we have 5 sites on the west side of the Sierra Nevada. The one in Yosemite National Park, we've deployed snow measurements for, this will be our 4th year. Sequoia National Park, 2 years, and the other sites, the other 3 sites we're just putting in right now. Collaboration with Department of Water Resources, water districts. We're measuring more than just snow. We're also measuring soil moisture, sap flow. We're actually putting up a flux tower in the mixed conifer. We're trying to provide both research quality data for advanced hydrologic models and water balance estimates in headwater catchments, but also data that can be tested with operational models too. Our measurement strategy relies on strategically placing instrument clusters to capture variability across the landscape and then blending that with satellite data. I'll show a few pictures from our prototype instrument cluster in Sequoia National Park. This is, anybody ever been to Wolverton Basin? Which is an old ski area, but it's not a ski area anymore. It's non-wilderness area, so the Park Service has let us put instrumentation in there. They're very, very good to work with. This is a topographic map of the basin. It's about 10 square kilometers. Goes from about, 7,200 feet, so a little above 2,100 meters, up to about 2,500 meters, or maybe a little higher up, and I can't read the numbers on here, in the higher elevations. We set up 2 water balance instrument clusters, one at a lower elevation, one at a higher elevation, to try to capture elevation differences in the basin. The instrument cluster, I'll show you what it has. It has met stations and snow measurements and soil moisture and so forth. Also, this actually has a huge meadow in it, so we're looking at groundwater surface water interactions in the meadow too, and with a lot of instrumentation. And we've added some stream gauge measurements in the basin. So try to get a water balance on this basin. This is the same strategy we're applying at all those smaller basins that we're instrumenting. This is the largest one we're instrumenting right now. And only 2 stations, and that we would rather have 10, but that unfortunately reflects our budget that we had, which was less than $100,000 for the instrumentation to put in here. But still, I think that we have started to cover the variable. This is the stream draining the basin, so this is during spring snowmelt in 2005 or 6, I forget, but anyway, one of the wetter years. There's a pressure transducer down in the stream, a nice natural. We look for natural control sections where possible instead of putting in flumes or something. We've put up some more meteorological stations just to get temperature, wind, radiation, so forth. Soil moisture, we dig pits down to 1 meter, put in, these are sensors, TDR, time domain reflectometry sensors. These are from Campbell. We're switching over to use ones from Decagon this year since they've become more mature. And part of our sampling strategy is to capture the variability in the basin. So elevation is one variable. Now, our understanding of where to sample comes from measuring snow, not from measuring soil moisture. There are basically no soil moisture measurements to base a sampling strategy on. So we base our sampling strategy on the variability of snowpack, and at a first hypothesis is that soil moisture will follow the snowpack. variability. So north-south aspect, huge differences in both snow and you can melt out at least a month faster on the south aspect than the north aspect. Soil moisture. Just anecdotally, you go out on a south-facing slope, it's really dry. North-facing slope, the soil's still moist. Well, we've done a few synoptic surveys to characterize that, together with my colleague Jan Hotmans from UC Davis, is a partner in the soil moisture measurements. Another one is where you are relative to the tree. Now, these are big trees. These are the Wolverton Basin is in basically the red fir zone, but there's also some white fir, some incense cedar, Jeffrey pine, and so forth. Whether you're under the canopy near the tree trunk, out at the drip edge, which is actually the wettest, or out in the open, which is dry, and under the canopy is often dry also. That's a huge difference in soil moisture and snowpack in many cases. And then not at this site, but another site, we're actually putting instrumentation under different trees to know. So you have a cluster of trees. We'll do an incense cedar here, a red fir here, a Jeffrey pine here. So we put in soil moisture and temperature. We put sap flow onto the trees. These are the snow pingers mounted on poles. These are acoustic depth sensors. So it sends a signal down, senses the depth to the ground. As the snow builds up, it senses the depth there. We just try to distribute these over the topographic variability, also physiographic variability, including putting one over every snow pit or soil pit. So this is a node, and there's 4 of these nodes in our Wolverton Basin, 2 north-facing, 2 south-facing at different elevations. In another basin we're instrumenting, I think we have money to put in 12, which is more the number we would like to put in to get the statistical variability. We think that 12 is enough to capture the variability across the 12 of these nodes across this size catchment for research purposes. This is just a picture. You can put wells in the ground, but you can't see anything except a little pipe sticking up. We instrument the meadows also to see where the water's going relative to the groundwater. I'll just mention briefly our transect. Instead of a basin in Yosemite National Park, we're doing a transect across Tioga Pass Road. Because in Yosemite, we're limited to working in the non-wilderness area, and there happens to be a 200-foot non-wilderness corridor on either side of the highway. So that is our observatory in Yosemite right now. And they even let us pour concrete and stuff in that non-wilderness corridor, but not to go beyond the 200-foot limit. But still, we can capture the topographic variability and physiographic variability in that corridor if we're clever about where we put things across this roughly 30-mile transect. Okay, we've tested. Now, where are we? In some of these sites, we're connecting sensors by wires because our sensor technology is not mature. Our wireless technology, the wireless technology is not mature enough. We got some really top-of-the-line sensors from a company called SensorNet, but they're way too expensive, and they want hundreds of thousands just to change something. So we're working with other colleagues who are building their own and trying to test them. I don't build sensors or communication technology. I apply them for earth science purposes. So this is an area, getting nodes that will connect sensors is a constraint right now in deploying these. The sensors are low enough cost, we can deploy lots of them, but connecting them together is still the problem. So we're testing a number of ways to do that. So, concluding thoughts, we need a better we need better methods for estimating water fluxes in reservoirs, especially in the Sierra Nevada, where climate change and other pressures have created a big demand for new knowledge. And the economic value of better information just for the water industry is huge. And we're finding water industry colleagues looking for ways to try to invest in some of this, but they keep asking the question, well, how mature is it? Is it reliable? Can I use it now, or do you need another few years of research before it's reliable enough for me to put out a forecast that people's livelihood depends upon? So these advances require sustained investments, and these better ground-based systems together with remote sensing are the way we get there. That's my message. Thanks.
Thanks so much, Roger. We have about 10 minutes for questions before the hour ends, and there's one in the back. Could you just identify yourself very quickly?
Tony Kane. To what degree are your errors systematic? That is, they will be consistent from year to year, and once you've established what the error is, you could actually depend a lot on current sensors and find it reliable. In other words, you put in a large sensor network and find out what the error is, and then you can pull out a lot of those sensors ultimately once you've found out what these readings you get actually mean, versus to what degree the error is random.
Exactly.
And that you can't determine from year to year, like how much blowing wind or rate of snowfall, that sort of thing.
In some cases, we see reproducible patterns from year to year. So we can go out and just do a one-time survey, or maybe 3 times during the year, and say, okay, based on this survey, we need to put sensors here, 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 and here. And we've come up with, you start narrowing your error bands as you go to more sensors. For one node, we came up with about 10. It really plateaus out, 10 snow sensors. If you go to 20, you're not going to get any better information. And I forget the magnitude of the uncertainty there. But we still need some multi-year data, because it's not clear that every year the patterns are reproducible from year to year. But still, we have identified areas that minimize the error, and I'd have to look back at our paper to see what the magnitude of those errors were.
Other questions? Here's one.
Norm Miller. Can you say a little bit about how one would go about correcting for below canopy snow errors and what might be needed as a first approximation other than just a lot more sensors?
I'm afraid I punted on that here in this talk, but what Norm is referring to is that when a satellite sees 50% snow cover in an area, is that actually 100% because the rest is occluded by the trees? And our data on there are not real consistent yet. In some cases, the fraction snow cover is less than what I have for canopy closure from existing Forest Service or Park Service data. And the Park Service data are the best available for canopy closure. So there are some other folks that are developing geometric models. You put in the tree height, the average canopy size, and then you take the satellite angle and you can calculate back. But I'm really pursuing a more empirical approach by instrumenting representative trees and trying to empirically establish the basically size of rings that are melted out around trees during different times of the year. So I haven't come out with it. We're still working on that. But I think the empirical approach is going to pay off almost as well as the physical modeling approach in this case. But nevertheless, my colleague Xinhua Guo at Arizona, where am I now? Merced. I used to be at Arizona. Colleague Xinhua Guo is getting LiDAR data over some of these areas, so we'll maybe be able to do that next year.
Les Ranke, if you take water balance, energy balance, snow measurements, and perhaps stream or reservoir measurements and correlate them, which is the best one to go further on?
Well, for the water balance, we need to start with the snowpack, because most of the precipitation in these headwater basins, most of the precipitation that produces runoff for hydropower and fill reservoirs is from snowpack. But for other purposes, soil moisture is the key response variable. Soil moisture is measured almost no place in the Sierra Nevada. We've put out about 100 soil moisture measurement probes. And then, of course, stream flow. And stream flow, there's different accuracies of stream flow. So our approach is to measure all 3 of those. And then at selected points, we're putting up one flux tower this summer to get evapotranspiration and turbulent exchange, carbon exchange with this canopy. But the problem is these trees are 50 meters tall. And then we're putting sap flow every place we put a soil moisture. So the idea is to try to get all the main components at representative sites and then use LiDAR remote sensing data to try to scale those across the landscape. So I don't have any one. It depends on what purpose but we're trying to get the process understanding and full water balance.
You've been doing this for a long time, presumably, and can you say anything about long-term trends that you might have spotted? You had general words here about the economic impact. I don't want to ask you to go into the quantitative meaning of that, but obviously it would have a tremendous impact to lose snowmelt the way you've predicted, perhaps.
Yeah.
But what about long-term trends? What's going on here?
Actually, long-term trends are not part of my research area, but I have a lot of good colleagues that do. But they're out there. I mean, if you look at the Pacific Northwest, the April 1st snowpack, which is the canonical peak snowpack, is half what it was when I was born, a little over 50 years ago. And we don't see the same trends in the Sierra Nevada, but my hypothesis is we don't have the right measurements to see the trends necessarily. And some other colleagues have come up with hints of trends. So, yeah, next question.
Okay, next question. Here's one. Sorry.
So I'm from civil and environment engineering. From my own experience, I observed the underestimation of physical models in snow simulation in Sierra Nevada. But I think the current snow pillow and the snow tell data is the one we can rely on. What is your option to overcome the canopy interception and to narrow the gaps between the physical models and your measurement network system?
Well, my strategy is to continue to rely on these snow pillows, maybe a couple hundred snow pillows, or 150 snow pillows, something like that in the Sierra Nevada, to give us density, because at those sites, and most of them, not all of them, there's measured both snow water equivalent and snow depth. So from that you get the density. Density is rather stationary. It doesn't vary across the landscape. Then I can put a lot of these snow depth sensors around at representative locations. And if possible, connect those in to the communications that's already at the snow pillows, so you can get the data out in real time. But then there are some other areas where there are no snow pillows. And actually, working with DWR, we've put in 3 or 4 new snow pillows. 5, actually. They're not all constructed yet, but we've put stakes in the ground where we're putting in 5 new snow pillows. So we're trying to close that gap slowly with DWR. So yeah, again, the strategy is to take those 100 or so, turn it into a couple thousand or 5,000, 10,000 snow depth measurements. Then you can get representative measurements that you need for your physical model.
That's going to be reasonable scale, but actually you are looking at smaller scales. When a larger number, like hundreds something snow pillow or snow tail sites.
And it's something like the Merced or Tuolumne River Basin, which are in the 2,000 to 4,000 square kilometer. At a research basin, I've spec'd out at least 100 for one of those basins for research purposes. But this Friday, I'm meeting with an operational agency that works on that has the San Joaquin River Basin. And I'm not sure what number I'm going to tell them yet because we haven't studied it, but it's at least 100 snow pingers, maybe 200.
Thank you.
These things are only $500 each.
Thank you.
One last question, perhaps?
So I was curious on the image interpolation that you're doing. I'm not sure I saw. What level of accuracy do you think you've achieved with that? I was curious because it seemed like the data had a lot of holes in it.
Yeah, we think the MODIS data are the best, and they actually correlate well with Landsat. We consider Landsat to be ground truth for getting snow-covered area. So what I showed you were the messy data stream before any filtering, because Jeff's doing the filtering and he hasn't passed me his filtered data yet. So just the data that we have. I think they're accurate enough, but how accurate in terms of snow-covered area, I don't know. I think the biggest uncertainty which probably introduces a 20 or 30% error in some areas, is the canopy correction. But I think I can narrow that to at least 10% or less with the empirical relations in terms of snow-covered area, maybe much smaller.
Great talk, Roger. Thank you very much. Obviously, a lot of interest here.
Thanks.
Really appreciate it.